Do you know that heart failure is the fastest growing cardiovascular disease in the world, with an estimated 64.34 million cases around the world and 6.2 million cases in the US? Heart failure is a clinical syndrome often characterized by structural abnormality in which the heart is unable to pump enough blood to meet the body's requirements. Its current treatments include surgical interventions and medications, which makes it an expensive disease to treat. In fact, in the year 2012, around $30.7 billion were expended on the treatment of heart failure across the US. Another concerning aspect is the increasing number of premature deaths due to heart failure, with up to 50% of heart failure deaths are sudden and unexpected. This high rate of sudden cardiac death due to heart failure is because, unlike other diseases, its symptoms are not very clear and obvious in its initial stages. Now, the question arises, is it possible to diagnose heart failure to make necessary interventions well in time? The answer is yes. In fact, not only its diagnosis is possible, but its prediction is also possible. My research is to predict heart failure by sensing significant biosignals related to heart failure. Important question is, which signals are significant? Literature shows that parameters like electrocardiogram ECG, heart rate, position analysis, and thoracic impedance, which is the impedance of the thorax region, are significant enough that if tracked continuously, then heart failure can be predicted at least 14 days before it actually occurs. But can current diagnostic tools of heart failure be useful for this purpose? The answer is no, because they are not capable to measure these parameters continuously, as they require trained physicians and admission into hospitals, which makes them very uneconomical and unfeasible. However, unlike traditional techniques, wearable technology has the potential to measure biosignals continuously and in real time. For this purpose, we have developed a wearable belt by embedding different sensors along with their integration in order to continuously measure the significant parameters related to heart failure. The belt can easily be worn at all times, as shown in the first figure. We have obtained some encouraging preliminary results for different real-time conditions, for example, sitting, standing, laying, and walking. Some of these results are shown in these graphs. The first graph shows the change in thoracic impedance while inhaling and exhaling in different conditions. As you expected, the thoracic impedance increases while inhaling and decreases while exhaling, which are in accordance with the literature results for thoracic impedance. Similarly, we have obtained clean and visible ECG results for stable conditions like sitting, standing, and laying, with expected motion noise while walking that can be filtered using signal processing techniques. We have shared these results on a user's smartphone using Bluetooth for him to visualize them in real time and to share with a concerned medical practitioner in order to make any necessary interventions. These recordings will then be used to develop an algorithm that can generate an alert whenever any one of these parameters crosses the defined safe threshold to predict the heart failure. Therefore, as part of the next step, we will now be conducting our clinical trials on a random set of patients in order to acquire data using a wearable belt so as to develop the algorithm.